In this lesson, we shall focus on mathematics, MAM2013S Abstract Algebra, Introductory Algebra. We shall actually go through the textbook's approach to the chapter on groups, and we shall explore, the textbook's approach to the TATs, the tutorial questions, and see if there are any similarities or if the textbook's approach is different. Okay, right. And we proceed as follows. Right, obviously we are looking at the section, the chapter on groups. And as usual, we are looking at the textbook's approach. So I want us to relax a little bit and not be so much in a haste to rush to the end, but to really say what is the textbook's approach to this particular section or chapter. We note that we begin our study of algebraic structures by investigating sets associated with single operations that satisfy certain reasonable axioms. That is, we want to define an operation on a set. This is very important. We define an operation on a set in a way that will generalize such familiar structures as the integers together with the single operation of addition. Right, so we're mentioning that we study the integers, but with the single operation of addition. Normally we look at the integers, but with addition. Or invertible 2x2 matrices together with the single operation of matrix multiplication. Normally we look at the integers together with the operation of addition, or the 2x2 matrices together with the respective single operations. Right, we said that the single operation of matrix multiplication. So when you look at the 2x2 matrices, we look at the matrix multiplication there. Okay, so this becomes so important. So we shall be looking at the groups that this book highlights, the groups that involve matrices, but involve the operation of matrix multiplication. So the integers and the 2x2 matrices, together with their respective single operations, are examples of algebraic structures known as groups. So far, the textbook highlights important structures, right? So what are these particular important structures? So the important structures become, you have the set of integers together with addition, right? So now they are the general linear groups, for instance, of 2x2 matrices, and with the operation of matrix multiplication, something of this sort, right? In which case, therefore, you can look at the GL2, you can even look at the GL2 because already it's square matrices. This GL2 with multiplication there. So in other words, you can actually be interested. Obviously, we shall be coming across the notations as we go along. But now, so far, the author of the book is really saying, let us take note of the group. We have the groups, this group of integers with the operation of addition, but also the 2x2 matrices with the operation of multiplication there. Next, the theory of groups occupies a central position in mathematics. Modern group theory, right? Modern group theory arose from an attempt to find the roots of a polynomial in terms of its coefficients. Right, so this is very important to say. How did group theory come about? How did this modern group theory come about? It arose from an attempt to find the roots of a polynomial in terms of its coefficients. Right, so obviously you see the roots of a polynomial, the one we know best, a polynomial of degree 2, we can be able to find the roots, right, in terms of its coefficients, because the mathematicians were motivated by this formula And they then said, okay, if ever really it is possible that we can be able to find the roots of this quadratic polynomial, because this is a polynomial, but it's a quadratic polynomial, right? So we are interested in finding the roots of this polynomial just in terms of its coefficients. So modern group theory always obviously arose from an attempt to find the roots of a polynomial in terms of its coefficients. Here is a polynomial. These are the roots, and there are two roots which can be distinct, which can be equal to each other, right? But they are in terms of the coefficients A, B, and C only. Very interesting. But groups now play a central role in such areas as coding theory, counting, and the study of symmetries. Right. Many areas of biology, chemistry, physics have benefited from group theory. Right. So we can actually testify, give of your testament to the fact that biology, chemistry, physics have benefited from the study of groups. I'm a physicist also, and I can actually be able to testify that indeed physics has actually substantially benefited from groups. But not only that, I'm also a chemist as well. And I can say that chemistry has also benefited. Just studying the orientations of the organic molecules in organic chemistry, obviously the orientations of those allows us to be in a position to then say group theory there enjoys a lot of applications in chemistry, and we proceed as follows. Now, there are certain things like your integer, equivalence classes, and symmetries. We are just discussing these because why? They are very important. Many times they appear as part of the exam. So because they appear as part of the exam paper, it's very important to understand these two sections, the integer equivalence classes and symmetries. Let us now investigate some mathematical structures that can be viewed as sets with single operations. We are looking at mathematical structures that can be viewed as sets with single operations. There's a mathematical structure which can be viewed as a set with a single operation, be it addition, and etc., etc. Okay, right. So this being the set of integers. So now let's look at integers modulo n, or integers mod n. Right. So the integers mod n have become indispensable in the theory and applications of algebra. So the integers mod n have really become indispensable, and they're part of this. Right. In mathematics, they are used in cryptography, coding theory, and detection of errors in identification codes. Okay, we pause to reason this a little bit, to digest this, and to internalize what the author is saying here. In saying in mathematics, they're used in what? In cryptography, coding theory, and the detection of errors in identification codes. So we see that the integers mod n have found a lot of applications just in mathematics alone. We have already seen that two integers, a and b, are equivalent, mod n, if n divides the difference. So the question becomes, when do we say two integers, a and b, are equivalent modulo n? So two integers, a and b, are actually equivalent modulo n, right? If n divides the difference, n divides a minus b, the integers mod n also partition z into different, right, into n different equivalence classes. Very important. So we say that two integers a and b are equivalent to each other, or with each other, modulo n, if n divides a minus b. So in other words, that means a minus b must be a multiple of n for the a minus b themselves to be equivalent, or for the a and b to be equivalent modulo n. Right, and also if a minus b, if n divides a minus b, then it means that a minus b becomes is equivalent to 0 modulo n. The integers mod n also partitions that into n different equivalence classes. So we're looking at partitions, and we really are saying the integers mod n have a tendency to partition z into n different equivalent classes. Mod n, modulo n, what does it do? The integers modulo n also partition the set of integers into n different equivalence classes. We will denote the set of these equivalence classes by z subscript n. Right, consider the integers modulo 12 and the corresponding partition of the integers. Okay, let's look at the integers modulo 12. In other words, we're looking at z subscript 12. And looking at z subscript 12, right, and the corresponding partition of the integers. Let's discuss the notion of the partition of the integers in what you call the integers. Here's the language. In the integers modulo 12. So now we're able to see that the equivalence clause, because we're looking at the equivalence clauses, the equivalent clause that contains 0, the integers that are equivalent to 0, and we're able to see that we have, because we're looking at integers modulo 12, then we can see the multiples of 12. Right, 12, 24, because 12 is actually equivalent to 0 modulo 12, and the multiples of 12, like 24, but not also just the multiples of 12, even the negative multiples of 12, right, are all equivalent to 0 modulo 12, meaning minus 12, minus 24, minus 36, minus 48, minus 60, and so on and so forth. In the same way, they also proceed in the positive direction. So you have 24, right, and you add 12 to that, you have 36, you have 48, you have exactly 60, and so on and so forth. But all these multiples of 12, because we are in integers modulo 12, are all equivalent to 0 modulo 12. Okay. There are those integers that are equivalent to 1 modulo 12. But now the set of integers is actually such that the integers modulo 12 also partitions z into n. Right, so in other words, in modulo 12, then we shall have 12 different equivalence classes. Right, so that, for instance, equivalent to 1 modulo 12 would be obviously the integers 1, because 1 is equivalent to 1 modulo 12. 13, it's equivalent to 1 modulo 12. And how do we know? Well, we look at the remainder. When this number 13 is divided by 12. So these sets are sets of remainders after division by 12, because you take 13, you divide it by 12, and 12 goes how many times it goes once, but we're looking at the remainder. The remainder is actually 1 out of 12, and obviously we're able to see therefore that 13 is equivalent to, in other words, 13 is equivalent to 1 modulo 12. Right, so and also we look at the next one, we have 25. 25 is also equivalent, because if you divide 25 by 12, the remainder is 1. Right, so now it is then very interesting. So if you then look at minus 11, right, so what is then minus 11? But minus 11 is also equivalent to 1 modulo 12. It's equivalent to 1 modulo 12. And a couple of ways to see that. It's when you can look at the 12 and you subtract 11 from it and you get 1. Right, so, and right, and also here you can subtract the largest multiples of what? You can subtract the largest multiples of 12. Here, 13, you can subtract 12 and you get that. And from 25, you can subtract 24. You get 1 and so on. And this continues to 11. And 11, the equivalence clause that that contains all integers that are equivalent to 11 modulo 12, this one here is actually such that it is the 12th one, because we're in modulo 12, so there are 12 equivalence classes, 1, 2, up to 11, so there are 12 of them. Now, Let us look at the integers equivalent to 11 modulo 12. What are they? So, right, 11 is equivalent to itself, modulo 12. Well, because the reason for that would be if you divide these 11, if you divide the 11 by 12, right, what do you get? It goes 0 times and the remainder is 11 out of 12. So we're looking at the remainder. So that obviously 11 is equivalent to 11 modulo 12. 23. Right. So now if you look at 23, so we're able to see that 23 now, if you look in modulo 12, what is 23 in modulo 12? So now you take modulo 12 and you divide by the right, you divide accordingly by 12, and you're able to see, therefore, that also 23 is equivalent to itself modulo 12. Okay, so that's something that is very important over here. Right, when no confusion can arise. Right, let me just speak to this person here. Right, yeah, let me just speak to this person here. Yes, hello. Yes, taken. It's done. It's done. Yeah, yeah. Okay, thanks. Okay, goodbye. Right, so when no confusion can arise, we'll use 0, 1, up to 11 to indicate the equivalence classes, like 0, 1, up to 11 respectively. That is when no confusion can arise. We can do arithmetic on Z subscript n for two integers a and b, define addition modulo n to be, right, so in other words, for two integers, a and b, we define addition to be what? For two integers a and b, we define addition to be a plus b modulo n. A plus b modulo n. That is the remainder. Well, very important. That is the remainder as we're doing division here, looking at the remainders. That is the remainder when a plus b is divided by n. Okay, well, just reviewing the textbook, just discussing some of the the author's approach, and then we shall be looking at the tabs after this, and we shall be solving the exercises in the textbook as well. Similarly, multiplication modulo n is defined as, right, so it's defined as ab modulo n. So with the two integers, you multiply them and you write ab and you write modulo n. Like this. The remainder when AB is divided by n. The remainder when AB is divided by n. The following examples illustrate integer arithmetic modulo n. The following examples illustrate integer arithmetic modulo n. Let's look at the integer arithmetic. For example, let's just recap on some arithmetic in the textbook here. Like, what is 7 plus 4 modulo n? Okay, so in other words, why is the author of the book saying modulo n? Because you can see it's modulo 5 here, it's modulo 8, modulo 12. So obviously the n sort of changes from one sort of example to the next. But now, obviously, we know that 7 plus 4 is actually 11. But now, if you take 11 and you then say modulo 5, so we need to look at the remainder when 11 is divided by 5, and we know that 5 goes how many times into 11? We know that 5 goes 2 times into 11, 1 out of 5. So, and 1 is the remainder, so that 7 plus 4 is 1. It's actually equivalent to 1 modulo 5. What is 3 plus 5? 3 plus 5 is 8. But 8, we know very well that 8 in modulo 8 would be 0. Why? Because you divide 8 by itself in modulo 8 and you get the quotient is 1, the remainder is 0 out of 8, and therefore, if you look at what 8 is, so obviously 8 becomes equivalent to 0 modulo 8. And yeah, all right. Now, what is 3 plus 4? 3 plus 4 is 7. In modulo 12, 7 is just 7. Why? Because in modulo 12, if you can wish to convert 7, you divide it by 12. 12 goes how many times into 7? Goes 0 times, and the remainder is 7 out of 12. So that obviously for the modulo, we look for the remainder. In the remainder, so 3 plus 4 becomes just 7 because That is the remainder when 7 is divided by 12, modulo 12. What is 7 by 3? 3. 7 times 3. So 7 times 3 then is equal to exactly what? It's 21, but in modulo 5, then we can see that the remainder is 1. In the same way, 3 by 5 becomes 15, but in modulo 8, if you take the 15 and divide by 8, for instance, 8 goes how many times there? We know very well that 8 goes once, and the remainder becomes exactly 7 out of 8, the divisor, and therefore we're able to see that 3 times 5 is actually equivalent to 7 modulo 8. Now 3 times 4 is 12, which is equivalent to 0 modulo 12. In particular, notice that it is possible that the product of two non-zero numbers modulo n can be equivalent to 0 modulo n. To 0 modulo n. Okay, so now let's actually just to obviously make sure we understand that. This last sentence here is very important. In particular, notice that it is possible that the product of two non-zero numbers modulo n can be equivalent to 0 modulo n. So yeah, you can take two integers that are two non-zero numbers, like in this 12. 3 and 4 are non-zero, but their product is 0. So yeah, you can multiply two non-zero numbers modulo n, and can be equivalent to 0 modulo n. So you can say, what is 3 times 4? 3 times 4 now it's 0 modulo 12. So yeah, that is what the author of the book is trying to bring across. I want us to recap on this example here as a very important one. In view of our multiplication table, we actually obviously picked up on the Cayley table, but also the sort of patterns that we can read off from this table in terms of can we be able to read off certain properties like your identity, your inverse, and so on and so forth from the Cayley table. It has to be possible, but let's just develop that skill by looking at some examples in the textbook. Like example 3.2, most but not all of the usual laws of arithmetic hold for addition and multiplication in modulo n. For instance, it is not necessarily true that there is a multiplicative inverse. For instance, it is not necessarily true that there is a multiplicative inverse. So in other words, sometimes it's not the case that there is a multiplicative inverse. Consider the multiplication table for Z sub 8, modulo 8, in figure 3.3. Notice that 2, 4, and 6 do not have multiplicative inverses. We're going to just check that one. Right, that is for n equals 2, 4, or 6, there is no integer k such that kn is equivalent to 1 modulo 8. Okay, now let's check. Let us check. Okay, now for example, we're looking at modulo 8, so modulo 8 can be written as, for instance, modulo 8 can be written as 0, 1, 2, 3, 4, 5, 6, 7. So we stop at 8 minus 1, which is 7. 8 minus 1, which is 7. And in general, for modulo n, we have 0, 1, 2, and so on. And we stop at n minus 1, like this. Right, so that in the end, then we have 0, 1, 2, 3, 4, 5, 6, 7. Then we have 0, 1, 2, etc. Okay, we have just put these elements horizontally and vertically. And obviously, we are investigating multiplication. Multiplication modulo n. So this is sort of the multiplication table for Z8. Right, let's check. Now, if you look at the fact that we have 0 by 0, it's 0, 0 by 1, it's 0, 0 by 2, it's 0, 0 by 3, up to 0 by 7, it's 0. 1 by 0, it's 0, 1 by 1, it's 1, 1 by 2, and so on. And last but not least, you have 7 by 0, which is actually 0. 7 by 1, it's 7. 7 by 2, okay, We analyze that one. So 7 by 2, for instance, is generally 14. But in modulo 8, we know very well that we shall have 6. Why? Because if you get 14 in modulo 8, you divide 14 by 8, and it goes how many times? It goes once, and then the remainder is 6 out of 8. And obviously now the modulo n becomes the remainder set of all remainders modulo 8, and therefore it's going to become a 6 here. All right. And obviously if you look at the 7 by 3, you would have obviously 7 by 3, you would say it's 21. But if you take 21 divided by 8, it becomes what? Right. So it becomes exactly 2 times, because this 8 divides 16. Right. So it divides 16, giving us 2 times. But if you look at the fact that divides 16, then you would have 5 more out of 8. So yeah, so that indeed 7 by 3 becomes actually 5 modulo 8. Okay, right. So, but the author of the book is making certain claims. Let us investigate and study the scalar table. But now, if we consider multiplication, the multiplication table modulo 8 in figure 3.3, notice that 2, 4, and 6 do not have multiplicative inverses. Let us check. So obviously, the multiplicative inverses will only be identified if only we are, here it is. Okay, and right, do not have multiplication inverses. That is, for n equals 2, 4, or 6, there is no integer k such that you can take the integer k and multiply it by n and get 1. So in other words, their inverse of n is that integer k, which when multiplied by n would yield 1 modulo 8. So, and obviously this comes after we must have identified the identity element. The identity element under multiplication becomes 1, and therefore when you multiply an element with its multiplicative inverse, you get the identity. Okay, right. And modulo 8. Okay, right. Now we can be able to see, let's look at it, let's investigate 2. So is there an integer that multiplies 2 so that we obtain a 1? We can multiply by 0, get 0, and indeed we can see that we can multiply, but there's no 1 here, meaning that there is no integer k such that kn is 1 modulo 8. Now, let us check 3. 3 by 3, it's 1. So in other words, 3 is its own inverse. But yeah, the examiner just spoke about 2, 4, also 4. Because 4, we multiply all of them, like 4 by 0, 4 by 1, 4 by 2, 4 by 3, and 4 by 7, but we do not get a 1. And therefore, it means that 4 has no multiplicative inverse, right? And this is what, so in other words, 2, 4, and 6 do not have multiplicative inverses, right? Whereas the others do, like 7 does have, because what is the multiplicative inverse of 7? The multiplicative inverse of 7 is 7, because 7 by 7 is equivalent to 1 modulo 8, like so. Okay, right. So yeah, we note that. But we note here with the fact that first we identify that in Z8, the element 1 is what? It's the multiplicative identity. This identity under multiplication, because it is when it multiplies all these integers such that the integers do not undergo any transformation in magnitude after multiplication by 1. We proceed just to check the textbook here. Okay, there's a proposition that is essential as part of the textbook's approach to this to this course, but also we're looking at what results sort of are very important here. Proposition 3.4. What does it say? You let Zn be the set of equivalence classes of the integers modulo n. Okay, Zn becomes the set of the equivalence classes, as we saw that earlier. And in other words, what does it mean? It means that if you look at the Zn, we can be able to write the Zn as 0, as 1, as 2, and so on, up to n minus 1, like that. So we can be able to write the Zn as a set of equivalence classes of the integers modulo n. And A, B, C are elements of Zn. Are elements of Zn. Addition and multiplication are commutative. Okay, this is very important. What is this proposition 3.4 about? In this proposition 3.4, we are saying we let Zn be the set of equivalence classes of integers modulo n. And we take the A, B, and C to just be 3. So we sort of extract 3 elements or members of Zn. Point number 1, addition and multiplication are commutative. So A plus B equals B plus A modulo n. That is, addition is commutative. Commutative means obviously you can change the order of addition, but also here multiplication means AB equals BA modulo n. Right, next point, addition and multiplication are associative. Right, so we can associate A and B, and this is equivalent to associating B and C modulo n, but also even with both addition and multiplication, so we actually can be able to say that multiplication is also associative, because if you have that the A and B associated, then it's the same as B and C associated modulo n. Right, they are both additive and multiplicative identities. So this proposition is very important. It gives Zn some structure, but it is really saying that both additive and multiplicative identities are there. So the additive identity and the multiplicative identity exists. So the 0 becomes our additive identity, because if you say A plus 0, we get A modulo n. So we have 0 as our additive identity, but also we have 1 as a multiplicative identity, because A by 1 becomes 0, becomes A by 1 becomes exactly A modulo n. Yeah, and the 1 is a multiplicative identity, and the 0 is our additive identity. Now, multiplication distributes over addition. Multiplication distributes over addition. Right. Multiplication distributes over addition. Multiplication distributes over addition. So that if we have A, the distribution A open bracket B plus C is equivalent to multiplication distributes over addition. So we have A, B, A, C. And this is true modulo n. Modulo n. So yeah, that is property 4. 5. For any integer A, there is an additive inverse, minus A. Okay, for any integer A, there's an additive inverse. Now, this is written in order, because for us to get the inverse, we must have first the identities. We must first have the additive identity and also the multiplicative identity. And then if we have the identities, then we can be able to speak of inverses, right? Because now we then say, for any integer A, there is an additive inverse, which is minus A. So the additive inverse of A becomes minus A, and therefore A minus A is it's obviously equivalent to 0 modulo n, 6. Right, let A be a non-zero integer. Let A be a non-zero integer. Then the greatest common divisor, the GCD of A and n, is actually equal to 1. So you take A to be, what is A actually? A is a non-zero integer, and the n is our usual index for the set Z modulo n. So now we then say, then the GCD of the A be a non-zero integer, and the n is equal to 1. It's equal to 1. When is you just take A to be a non-zero integer. Can be anything. Non-zero integer, like 1 billion, 2, 3, 4, random number. Then the greatest common divisor between these random integer and n is 1. When is it 1? It is 1 if and only if there exists a multiplicative inverse B for A modulo n. That is a non-zero integer B such that this is the case. Okay, let us continue and check these carefully. Let us continue and check these carefully. We continue and check these carefully. Okay, we continue, please. I want us to just understand 6 quite well. I want us to understand 6 quite well. So first with 6, we start with a random integer, and we are dealing with a random integer a, and right, and we're saying it is not 0, and obviously it is an integer. So being an integer means that in principle a is an element of z. So let a be a non-zero integer. Then the greatest common divisor of the non-zero integer a together with the index n is 1. When is it 1? If and only if. What is the necessary and sufficient? Necessary and sufficient condition for the greatest common divisor to be 1. It is true if and only if, it is 1 if and only if there exists a multiplicative inverse b for a modulo n. That is a non-zero integer b such that ab is equivalent to 1 modulo n. So take note of that. So in other words, this greatest common divisor is only 1 if and only if there exists an inverse, a multiplicative inverse b for a modulo n, such that that is a non-zero integer b, so that when you multiply the random integer a by the b, then you get 1 modulo n. Okay, we sort of get the point. We will prove, we can give examples. That becomes the best way to sort of obviously. We shall look at examples of this. We will prove 1 and 6 and leave the remaining properties to be proven in the exercises. That's okay, right? What is 1, for example? 1 is that addition and multiplication are associative. So a commutative, excuse. So that a plus b is b plus a modulo n, but also ab is ba. So we're proving commutativity of addition and multiplication. Now, addition and multiplication are commutative modulo n since the remainder. A plus b divided by n is the same as the remainder. B plus a divided by n. Okay, look at how this author of the book proved this here, because we shall be using this in the tasks, but we shall be using this in the textbook exercises. But the question is, how would you prove the commutativity? This is the proof. Addition and the multiplication are commutative modulo n. Why? Since the remainder of a plus b divided by n is the same as the remainder of b plus a divided by n. Yo, so this guy is saying, hang on, the remainder of a plus b divided by n is about remainders. It's about remainders. The strength of the proof is about remainders. So a plus b will have the a plus b divided by n. You're dividing. The remainder of a plus b divided by n is the same as the remainder of b plus a divided by n. Something important. Okay, so yeah, this means therefore, and obviously, and this guy went on to then say addition multiplication are commutative modulo n, and we have that. Okay, did the guy prove 1? He didn't prove 1. He or she, the author of the book, did not prove 1 in full, because 1 is about indeed addition multiplication, but you can see there's a plus b, which must be b plus a modulo n, ab must be a modulo n, but you can see the author of the book did not. I've taken this is the book, but I've taken this from the book, and I can tell you that indeed did not prove, because there's no AB. So the author was also supposed to say AB divided by n is the same as the remainder of BA divided by n. the remainder of AB divided by N is the same as the remainder of BA divided by N, and therefore that means that AB is equal to BA modulo N. Okay, now we're going to check do property 6. Right, so suppose that the greatest common divisor of A and N is 1, then there exists integers, okay, by divisibility, by the division algorithm. We have to spend time on the division algorithm, but this guy is starting the proof by looking at the fact that, okay, we suppose that the GCD of A and N is 1. Then there exists integers R and S. R and S. Such that AR plus, take this A, so we take the A and you multiply, so there exists integers A and R, and then N and S, N times S, so that the result is 1. Because the greatest common divisor is 1, then it means that you can be able to write this linear combination. Let's manipulate this algebraically. Since now we can make NS the subject of this equation, make the NS the subject. So we move AR to the other side, so that NS is equal to 1 minus AR. It must be the case that AR is actually congruent or equivalent to 1 modulo N. Right, so this is very, very interesting. This is very, very interesting. So we are saying there exist those integers R and S so that AR plus NS is 1. Now, we continue. We continue. Okay, I'm taking a deep breath because I want us to analyze this. The fact that, of course, this is true from the division algorithm, but I want us to look at the algebraic manipulation and then say, let's make NS the subject, and therefore NS becomes equal to 1 minus AR. And the author of the book goes on to then say, it must be the case that AR is equivalent to 1 modulo N. Why is this the case? Why is this the case? It is the case because we're writing NS is 1 minus. Okay, it's one of the tasks. We're going to analyze the proof there. Right, so because we're dealing with modulo words, we're dealing with modulo N, so this part is going to be 0, modulo N. And if this part is 0, modulo N, then we have that this is like 0, 1 minus AR modulo N. And if this is 0, then it means that AR is 1. And that is why this is the case. But it's not just as AR is 1. AR is equivalent to 1 modulo N under the function of the modulo N. Okay, we continue. Let B be the equivalent class of R. We take B, or letting B to be the equivalence class of R. AB equals 1 modulo N. Right. So this would be true. So if you take B to be the equivalence class of R, from this equation, letting B to be the equivalence class of R, AR is already 1, so B is the equivalence class of R. So indeed it will follow that AB is 1. Because this B is in the equivalence class of R, so right, so B and R are equivalent modulo N, so that if the R can be replaced by B, modulo N. But we're saying B be the equivalence class of R. Okay, so obviously because we can see that this one here is a necessary and sufficient condition statement, meaning that we have proven, we started with the GCD equals 1, so we have proven the forward direction, the implication, and then it has to be true that we need to prove the converse. We need to prove the converse. Conversely, suppose that there exists an integer B suppose that there exists an integer b such that, so we're starting from the end of this, so we are starting from this, so we're starting saying, we suppose that ab is 1. Ab is equivalent to 1 modulo n, or is congruent to 1 modulo n, starting from the conclusion, and we want to establish the premise now. Right, so then n divides what? Because if AB is it's actually, you know, equivalent to 1 modulo n, then we can move the 1 to the left, to the side of the AB, so the 1 becomes negative. So it means, therefore, then n divides AB minus 1. So there is an integer k. So there is an integer k such that AB minus nk is equal to 1. So there is an integer k such that AB minus nk is equal to 1. Why is this the case? Why is this the case? Because we're dealing with modulo n, and we're dealing with a minus b. We're saying n divides a minus b. If n divides a minus b, then we are adding, therefore, the nk with the understanding, therefore, that this particular minus nk that has been now put here is equivalent to 0 modulo n, which does not quite alter this particular expression. Let, therefore, from this here, let the greatest common divisor of the a and the n be d, like a divisor. Since d must divide ab minus nk, d must also divide 1. Yeah. D divides this ab minus nk. It must also divide 1 because they're equal to each other. Hence, d is 1. Yeah, d is 1 because what other number really can divide 1? It's just 1 itself. 2 can't, 3 can't, and so on, so it just be 1. So that the greatest common divisor is 1. So yeah, we have 1. We have exactly 1. So we've been able to establish these here with so much ease and simplicity. We continue and we look at the next. Right, we look at the next result. Okay, now for a second, reason these, I'm giving you a minute to reflect on these, just 1 minute to reflect on these, and we shall continue in the next 1 minute. Come on. All right. Right, we shall continue the next 1 minute. Right, we are continuing the next 1 minute. Grab a glass of water, drink a little bit, and we shall continue the next 1 minute. Yes, fine. Where have you been? All right. Yeah, I'm just in my class now. Right, we are going on. We are continuing. We are continuing. Right, I was just speaking to another student. It's not that I just paused. I was just speaking to another student. So please forgive me. I was just speaking to somebody. So please do not say I just paused. I did not just pause. I paused because somebody was knocking on my door and I had to address them. And then now that I've addressed them, then we are going on. Okay, so yeah, we're good. We are going on. Yeah. Okay, yeah. So let's go on. Right, so I'm looking at the next thing now. And right, the notion of symmetries obviously emerges as very, very important in this section on groups. And let us discuss symmetries. Like at this point, we're discussing these particular symmetries as indicated. These are in figure 3.5, rigid motions of a rectangle. Let's look at the rigid motions of a rectangle. But first things first. Okay, the identity property. So now, or the fact that we're looking at rigid motions of a rectangle. So there is a rigid motion that is the identity. So it maps it maps this rectangle to itself, onto itself, so that in the end, then A goes to A, B, C to itself, and D to itself. So obviously, this actually here becomes sort of the identity symmetry, or the identity rigid motion. Let's look at their 180-degree rotation. Let's look at a 180-degree rotation. So at this point, if we rotate these by 180 degrees, let's see what happens here. So we can see that here's our A, and our A is now here. And let's look at our B. Our B is actually now there. Right, so what has happened? So let's check together. So if you look very carefully, this A has gone and is now sitting in that position. Right. And also similarly, you can look at the fact that this A has gone, is now sitting in that position, which is the most accurate transformation, because we shall be looking at most of these will be counterclockwise. Counterclockwise rotations. Counterclockwise rotations. So that in the end, then you have the A. All right, if then we are looking at the 180-degree rotation, so you can look at the fact that you have exactly that. Okay, right, so you have this one here, and you have this one vertically. Okay, and this is an angle of 90 degrees. Let's analyze this together a little bit. So, right, so, I mean, you're looking at the symmetries. So now, if you look at this here, you want to sort of identify what happens. So looking at a 180-degree rotation. So if you rotate these now, here it's the A, right? And if you are therefore to rotate these through 180 degrees in a counterclockwise direction. So what actually do we have first? So if you rotate through 90 degrees, right, so if you rotate through 90 degrees, this is actually what you're going to have. So you rotate this shape through 90 degrees, what would we get? So let's look. This angle is 90 degrees here. If you rotate through 90, you just look at a part of this rectangle, maybe this part here, and this vertical line. So now you then say, if you rotate it about the origin, you'd have this is going to move here and be here. So it's going to take, so this A is going to be sitting there. And then now, because it's 180 degrees, you'd have to rotate again another 90. And that is why obviously it becomes there. But if you do that, yeah, if you move the A, therefore it's going to be here, 1, 2. Then the B is going to follow suit. So obviously in the same way, so this is A, B, C, D. And therefore, you actually would be in a position to see that your A would be here, would have moved 1, 2 places. The B would have moved 1, 2 places. The C would have moved 1, 2 places. And the D would have moved 1, 2 places. And the D is going to be sitting there. Okay, let's move on to the next transformation. Okay, now at this point, let's look at the reflection vertical axis. Right, so in other words, if you look at the reflection in the vertical axis, reflection in the vertical axis that sort of cuts through in the middle. cut through the middle. But here becomes a reflection. So what does the reflection mean? Well, the reflection would be saying that you want to look for the image. So if your mirror is facing A like this, so you see that A is going to have it's going to be there, and B it's going to be there. C it's going to be there, and D it's going to be there. Because if your mirror is facing C, then your C is going to be inside the mirror. Then if you put your mirror to face D, and D is going to appear inside the mirror, so that D is going to be there. So if you put your mirror to face A, so your A is going to be inside the mirror. If you put your mirror to face B, so B is going to be inside the mirror. So in other words, you're dealing with the reflection along what you call the vertical axis. But now let us look at reflection horizontal axis. Right, a reflection horizontal axis, so you can have this reflection. So A goes there, and D goes in the opposite. Okay, so this is what you're going to have. So A goes there, and D goes in the opposite. Right, so obviously if you put your mirror to face A, so yeah, your A is going to be actually inside the mirror. But if your mirror faces D, then D is going to be inside the mirror. It's going to be there. In the same way, your mirror faces B, B appears inside the mirror. So if your mirror faces C, your C appears inside the mirror. So this sort of becomes a reflection in the horizontal axis. So obviously, what is this? Okay, I want us to note that we have one, 2. Okay. Then 3, 4. 4 symmetries. Right, we're looking at the symmetries of a rectangle. Rigid motions of a rectangle. So there are 4 symmetries. Rigid motions of a rectangle. So we have seen that there are 4 rigid motions of a rectangle. What are they? First, the identity rigid motion. And so that fixes, the identity fixes the rectangle in its original position. Right, and then we have the 180-degree rotation. We've discussed it. And then we have the reflection in the vertical axis. We've discussed it. And also the reflection in the horizontal axis. These are called rigid motions of a rectangle. We have seen counted 4 rigid motions of a rectangle. Okay, let us look at what the textbook's analysis of these becomes for a rectangle. So a symmetry of a geometric figure is a rearrangement. A symmetry of a geometric figure is a rearrangement of the figure, preserving the arrangement of its sides. So there's something you're preserving here. In the process of rearrangement, we are preserving the arrangement of its sides and vertices, as well as its distances and angles. So this is it. So in studying the symmetry of a geometric figure, so it's a symmetry of a geometric figure is a rearrangement of the figure like we saw, but preserving the arrangement of its sides and vertices, as well as its distances and angles. A map from the plane to itself, preserving the symmetry of an object, is called a rigid motion. What is a rigid motion? Okay, sometimes mathematics say they don't ask these definitions. Somebody would ask, what is a rigid motion in an exam? But they won't ask that mostly because they think it's too basic. But some students can even overlook that. But a map from a plane to itself, preserving the symmetry of an object, is called a rigid motion. It's a map from a plane to itself. This map preserves the symmetry of an object. Preserve, what does it mean to say it preserves the symmetry? It preserves the symmetry. It means that after the map, the object looks the same. So the symmetry is preserved. For example, if we look at the rectangle in figure 3.5, okay, we're looking at the rectangle in figure 3.5. The one we just looked at right now here, it is easy to see that a rotation of 180 degrees or 360 degrees returns, okay, 180 degrees, 360 degrees, returns a rectangle in the plane with the same orientation as the original rectangle and the same relationship among the vertices. Same relationship amongst the vertices. So the same relationship, what does it mean, same relationship among the vertices? So yeah, we see that the adjacent vertices remain adjacent still in the new shape. Adjacency is sort of preserved. A reflection of the rectangle across either the vertical, we discussed a reflection across either the vertical axis or horizontal axis can also be seen to be a symmetry. Okay, it is a symmetry. If we obviously look at the reflection, a reflection of the rectangle across either the vertical axis or the horizontal axis can also be seen to be a symmetry. Can also be seen to be a symmetry. Can also be seen to be a symmetry. We continue. We continue. However, a 90-degree rotation, in either direction cannot be a symmetry unless the rectangle is a square. Okay, so however, a 90-degree rotation in either direction, well, this is very important. A 90-degree rotation in either direction. So a 90-degree rotation in either clockwise or counterclockwise direction cannot be a symmetry unless the rectangle is a square. And obviously, I mean, that would be very, very obvious, because if you look at the fact that if you have this rectangle is like, it's like a strip. It's like a strip like this. But if you rotate through 90 degrees, it's going to produce a strip that is vertical like this. Obviously, my drawing does not look vertical, but the strip is going to be like vertical, so it's not going to produce an identical sort of shape there. So it's not going to be a rigid motion. So it's not a rigid motion for the rectangle. Let's continue. Okay, now something very important for us to take into account are the symmetries of a rectangle. So yeah, we shall discuss these ones, but in figure 3.6, which is the figure we're looking at, we're discussing the symmetries of a rectangle. Symmetries of a rectangle. Let's take a look at the symmetries of a rectangle. If you look at the of a triangle, excuse symmetries of a triangle, right? We're looking at the symmetries of a triangle, right? Now let's look at this. If it is ABC, okay, so you can see the way in which the author of the book labels these vertices is labeling them in a clockwise direction. So you have ABC like in the direction of a clock, ABC. The identity rigid motion, because we're dealing with the symmetries, what you call the identity symmetry. The identity symmetry, what does it do? It fixes the vertices. A is fixed, C is fixed, B is fixed. So all the vertices are fixed, and this is called the identity symmetry. It is called the identity symmetry. Okay, so you're able to see, therefore, that in the identity symmetry, this is fixed here. Okay, yeah, this person is trying to call their mind. All right, so A goes to A, B goes to B, C goes to C. You can see that each of these vertices is fixed. Okay, right. Each of these vertices is fixed here. Right, Trondre? Trondre? Yes, Trondre? Yes, okay, I'm in class now. Let me talk to you after my class. Yeah, I'm in class, but I'm going to be in class until 10 at night. Until 10 o'clock at night. And yes, until 10 at night. Okay. Right, yeah. Okay, never mind. Right, so now you have A is fixed, B is fixed, C is fixed. So all these vertices are fixed. Because all these vertices are fixed, what we're then actually getting to realize, therefore, is that Your A is fixed, your B is fixed, and C, yeah. So A goes to A, B goes to B, C goes to C, and this is the identity symmetry or the identity rigid motion. Now let us look at a rotation. So there are certain rotations that we're able to obviously determine here. Yeah, so we can look at the rotations either way. So yeah, but you know, counterclockwise rotations for us are natural in mathematics because they are you know, producing sort of positive orientations. Otherwise, we have negative orientations, right? So it is in the positive sense, right? So now, if you look at the ABC, what has happened right now? You can see that the A has gone, okay? So if you look at this kind of rotation, there are a couple of ways to obviously look at that. So if you look at the fact that now A is here, B is there, C is there, okay? Doesn't matter. If you look at it clockwise, for example, such that A goes to B, right? So that wherever there is A is going to be sitting in the position of B. B now is sort of is going to rotate to the position of C. C is going to take the position of A. Let's check. So A goes to B, B goes to C, and then C goes to A. Okay, so sort of we're able to see that this person who wrote the book obviously looks at the kinds of rotations that are like clockwise, the direction of the clock. So you notice that. Meaning even in the earlier part, we can mention in passing, if in the earlier part, you can always look at these rotations in a clockwise sense, like a clock. Okay, right. So that A goes to B, B goes to C, and C goes to A. Next. Let's look at another possible rotation. So now, in this possible rotation, let's look at A. A is here, but now A is there. Okay, looking at things the clockwise way, let us see. So this one A would have gone to B, and then B would have gone to C. So you'd have, like here you rotated once, and then here you would have rotated twice. A goes to B, B goes to C, so that A is here. B go to C, and then B would actually also go to the position of A there. Right. So, and now let's start. A goes to B, B goes to C. So in other words, A would have gone to C. Okay, we're done with A, because A, we can see that A has gone to the position of where C was. B would have gone to the position of what? B would have gone to this position, and that is the position of A. But that would take 1, 2. Okay, and then now C would have gone 1, 2. C goes to B. C goes to B. Okay, now, okay, let's check. So this would be obviously, no, those two rotations. Here, you'd have like a single rotation. Right, so here you'd have a single rotation, but here you'd have like two rotations. Right, two rotations. Let's check. Okay, and this is very, very interesting then, because we have these. Are these rigid motions? Are these rotations themselves sort of rigid motions? Well, they are rigid motions, but let's continue. Let's look at 3 reflections. We've seen 2 rotations, but now, yeah. Why did you not look at 3 rotations? Why not looking at 3 rotations? Because what would 3 rotations do? Okay, we looked at 2 rotations of the triangle, but why not 3? Because we understand it possible to get us to the identity. Let's check. Let us rotate this triangle 3 times. So obviously we rotated twice here to this point. Then let's rotate it 1 more time clockwise. So A would go here, which is the original. or the original. And then B would go here, which is the original. C would go there, which is the original. So 3 rotations would be like the identity. So there's no point. So that's why 2 rotations are enough for the triangle, right? We've seen that a 3rd rotation would be the same as the identity rigid motion. Okay, dealing with reflections. Dealing with reflections. Now, dealing with reflections. So what do we have here? Dealing with reflections. So now we have, for example, where is the A? A is here, but you can see A is there. B has gone there. And B has like gone down. And C has like gone up. So it's only A that is fixed. It's only A that is fixed. So what kind of a reflection would this be? What kind of a reflection would this be? Reflection along which axis? Right, so you can imagine that one possible reflection would be along this axis here. Right, if you reflect along this axis here, such that this is perpendicular, such that you have a bisector, this is a bisector, this axis that bisects sort of, right, you're able to see that your B would go there and your C would go there. And your A remains fixed. So A goes to A, B goes to C, and then C goes to B. And C goes to B. And we call that on mu1. Okay, let us look at another reflection. This kind of reflection right now, let's look at what it does this. So we're studying the reflections of a triangle. The sort of, reflections of a triangle, which are symmetries of a triangle. Right, so at this point, you can see that the C was here, but the C now has gone there, the A. So, but the B is fixed. So in other words, you can look at it this way. Okay, if you perform a reflection along a vertical axis, like that, B is fixed. A goes to C. C goes to A. A goes to C. We can see that A is in the place of C now. C has gone to the place of A. So let's check. A goes to C. C goes to A. B is fixed. So B goes to B because B is in the same position. But this would be obviously a reflection in the vertical axis. Let us check this one here. Which one is fixed now? We're able to see that C is fixed, but A goes to B and B goes to A. And so this is the one. So now we perform a reflection along this particular axis that sort of bisects like this. Bisects like that. It need not be really perpendicular, but it bisects. It bisects. So if it bisects, what then are we able to achieve? Right, C is fixed, but we're able to see that A goes to B. A goes to B, B goes to A, but C is fixed. Okay, so we really can see that with the reflections of a triangle, we are looking at the slanted lines, okay, slanted, but also the vertical. Can you look at a horizontal? No, there cannot be a horizontal reflection for triangles because it's gonna make the triangle upside down. Because if ever I would wish to reflect along this, then the B would go there, the A and the C would go up, and the triangle would be like would be flipped. So it's not a symmetry, that one, because it's producing an image that does not sort of preserve the actual that it does not make the image to look to appear as the original triangle anyway. So you don't have preservation of the distances there. Okay, we continue. So yeah, so now let's summarize. Two rotations, one identity, three reflections. You have 6 symmetries of a triangle. 6 symmetries of a triangle. 6 symmetries of a triangle. Okay, we've seen the 6 symmetries of a triangle. Okay, we're here to solve problems involving these things, but we're just passing through a textbook to see the approach. But you really can see that this textbook's approach views the rotations as clockwise, mostly. And that is what we've seen. And now for the triangle, we have reflections along certain diagonals like this. And this one with a positive slope, and this one with a negative slope, and vertical reflection. And we also have the identity that fixes all these vertices, but also we have the rotations. On these rotations, we have a single rotation and also double 2 rotations, in which case, therefore, we don't have 3 rotations for the triangle. Why? Because 3 rotations would be like the identity. We saw that. So if we performed 2 rotations here, but if you do one more, then you get the identity rotation there, or the identity map or symmetry. Okay, now let us say the following here according to the author of the book. Let us find the symmetries of the equilateral triangle. Triangle ABC. To find the symmetry of triangle ABC, we must first examine the permutations of the vertices A, B, and C, and then ask if a permutation extends to a symmetry of the rectangle. So first we examine permutations, and then we actually tend to ask ourselves if a permutation of the vertices extends to a symmetry of the rectangle. Recall that a permutation of a set S is a 1-to-1 and onto map. This is it. A permutation of a set S is a 1-to-1 and onto map. Pi from S to itself. From S to itself. From S to itself. The 3 vertices of a triangle produce, this is powerful, 3 vertices of a triangle produce exactly 3 factorial, which is 6 permutations. We saw there are 6 permutations for the triangle, right? We saw 3 reflections, 2 rotations, and the identity symmetry. Okay, we continue. Okay, I want us to have a brief discussion about some of the things that matter. Like, so the triangle has at most 6 symmetries. So the triangle has at most 6 symmetries. To see that there are 6 permutations, observe. There are 3 different possibilities for the first vertex and 2 for the second. And the remaining vertex is determined by the placement of the first 2. So we have, okay, this is very important. To see that there are 6 permutations, how do we see that there are 6 permutations of a triangle? For the triangle has 6 symmetries. To see that there are 6 permutations, observe that there are 3 different possibilities. 3 different possibilities for the first vertex, and 2 for the second, and the remaining vertex is determined by the placement of the first 2. So in other words, there are 3 times 2 times 1, which is 3 factorial, which is 6. Okay, 3 times 2 is 6 by 1, 6. Anyhow, different arrangements. Okay, we're going to spend a bit more time on this. But to denote the permutation of the vertices of an equilateral triangle that sends A to B, B to C, C to A, we write the array A to B, B to C, C to A. Notice that this particular permutation corresponds to the rigid motion of rotating the triangle by 120 degrees in a clockwise direction. In fact, every permutation gives rise to a symmetry of the rectangle. In fact, every permutation gives rise to a symmetry of the rectangle. Okay. Right. In fact, every permutation gives rise to a symmetry of the rectangle. All of these symmetries are shown in figure 3.6. We saw that. We saw that. 3.6, we saw that. Okay. We're just going through the author of the book's analysis. A natural question to ask is what happens if one motion of the triangle ABC is followed by another? Which symmetry is, yes. So the author of the book is then saying, which symmetry is mu1 rho 1? That is what happens when we do the permutation rho 1 and then permutation mu1. We do first, okay, if you write like this, we do first rho 1 and then we do mu1. Remember that we are composing functions here. Although we usually multiply. Okay, please check the time. I need to check the time. Okay, good. I want to do this. Okay, just 1 minute. I'm just speaking to this person here. So, I want to go to the groups. And now, right, just 1 minute. I'm just speaking to this person. Then I'm going to be right back. Okay, on these groups, you see there these groups. You need to paste this one. Paste this one on the groups. See this link on the groups. What are the groups? This one, this one, this one, this one, that one, that one, this one, up to that one. You get the point. It's there already. Okay, let me see. Yeah, tap here. Yeah, tap like this. But allow it, then you do this. Then it is there. Okay, but all of them. Okay. Right. So which symmetry? Sorry, I was speaking to someone here. So which symmetry is mu1 rho 1? That is what happens when we do the permutations rho 1 and then the permutation mu1. We do rho 1 and then do the permutation mu1. Remember that we are composing functions here. Although we usually multiply left to right, we compose functions right to left. So yeah, the functions like go in the opposite when you compose them. Right, so we compose functions right to left. Remember that we are composing functions here. Although we usually multiply left to right, we compose functions right to left. So yeah, if this is the right side, we start with this one, then we come to this one. So this is like the first one, and this is like the second function. So we compose functions from right to left. We have, okay, let's look at this one. If you look at mu1 rho 1 of A, so now in terms of the functions, this would be the same as mu1 in brackets rho 1A. And then what is rho 1? Right, rho 1 on A. Okay, we take rho 1. What does it do on A? Right, rho 1 on A, rho 1 takes A to B. Right, so that's what we saw. So rho 1 takes A to B. And then what does mu1 do to B? Right, let's check mu1. Mu1, what does it do to B? Mu1 takes B to C. Mu1 of B goes to C. So mu1 of B goes to C. Mu1 of B goes to C, and that is why this is true. Let us check. We're just composing these randomly. So we're doing mu1 rho 1 of B. Right, so obviously mu1 rho 1 of B is going to be mu1 rho 1 of B. Okay, okay, all right. They are right, good. All right, we good, good, good. Let's see, let's see, let's see, let's see, let's see, let's see. Even this one. Because okay, yeah, just talking to someone. This one, you know, you need to do that. All right. So now if you look at mu1 row 1 of B, so you have that mu1 row 1 of B. What is row 1 of B? Let's check. What does row 1 do? Okay, now row 1, obviously we saw that row 1 is what? Row 1 is a single rotation. Row 2 is like 2 rotations. So row 1 of B goes to C. Okay. Row 1 of B goes to C. Then mu1 of C goes to B. This is the same symmetry as, anyway, I'm just saying the next one is going to be done the same fashion, right? So this is the same symmetry as mu2, right? So you can do the same. You can put mu2, mu2, mu2 and do the same. Suppose we do these motions in the opposite order. Row 1, then mu1. Okay, so you can change the order because we did mu1, row 1, mu1. We can do row 1, mu1. See what happens. It is easy to determine that this is the same as the symmetry mu3. Can determine that this one here, for instance, we saw that mu1 row 1 is the same as mu1. Okay, look, and obviously it produced mu1, but I want to mention something here. It produced mu1, but what? And then it produced C. And the examiner or the author of the book was quick to say, this is the same symmetry as mu2. Because now you can see that, okay, what does mu2 does? So there's something that takes A to C, B to B, C to A to C, which one? But fixes B, and then C goes to A to C. Let's check. Right, so A to C, C to A, but fixes B, it is mu2. So in other words, if you combine, right, so if you combine mu1 and row 1, what you get is mu2. Is mu2. Right, suppose we do these rotations in the opposite order, row 1, then mu1. It is easy to, right, good, all right. It is easy to determine that this is the same as the symmetry mu3. Hence, we are able to see that whenever we do row 1, mu1 is different from doing mu1 row 1. Okay, because mu1 row 1, what is mu1 row 1? Mu1 row 1 is mu2. So this one is mu2. But what is row 1 mu1? Right, so it is determined that this is the same as the symmetry mu3. If we do these motions in the opposite order, if you do in the opposite order, it produces mu3. Yet mu3 and mu2 are different. Mu2 and mu3 are different because this one is CBA. This is BAC. So these mu2 and that are totally not equal to each other. Right, sir, yeah. Okay, now it is, yeah, hence that. A multiplication table. Let's look at a multiplication table, which is a Cayley table. And obviously the TAT you sent to me is about the Cayley table, but some general properties. We shall discuss the TATs in our next meeting. Right, so a multiplication table for the symmetries of an equilateral triangle is given in 3.7. Okay, we shall check figure 3.7. Notice that in the multiplication table for the symmetries of an equilateral triangle, for every motion of the triangle, alpha, there is, right, so, okay, good. Right, need to check this one here. Okay, need to check this one up to, okay, something I want to show you here. Right, so go to Sunday. Okay, and then you go to Saturday. Go to Saturday. Okay, there's something I want to show you there. Right, we go further to this one here. Okay, I'll show you. Right. Let's see something I want to show you quickly. Right, so you take this. Okay, yeah. We are going on, please. Yeah, just just directing you here. That just directing this student here. Okay, yeah. You take this one. So is this one here? Okay, yeah. So this one, you must also paste it on those groups. Okay, so notice that in the multiplication table for the symmetries of an equilateral triangle, for every motion of the triangle alpha, there is another motion beta, such that alpha beta is the identity. So you can be able to say, okay, alpha beta, there are two motions so that alpha beta produces an identity. That is, for every motion, there is another motion that takes the triangle back to its original orientation. For every motion, for every motion beta, there's another one that takes the triangle back to its original orientation. And that obviously sort of becomes the inverse. Okay, let's just look at the symmetries of an equilateral triangle here. Right, we are looking at the fact that this equilateral triangle, we saw that it has the identity. There are two rotations, single rotation. So this row one, we saw that is just one rotation. And then we saw that row two became two rotations. And then mu1, mu2, mu3, these became reflections. All right, so now, but we put them here on the horizontal and then we put them on the vertical. Now, if we do the composition, the Cayley table we're doing here because there's a part where we're going to discuss, prove some general result about the Cayley tables. But now we'll do the Cayley table for the symmetries of a triangle, and then we'll be like, okay, if you take the composition of the identity with identity is identity. The identity is with this, it does not change all these. So identity with mu3 is not going to change anything. But now this one need to check very carefully. Mu1 with identity symmetry is row 1. But row 1 with row 1 is row 2. Right. So if you do row 1, it is row 2. Right, so we have already discussed the fact that we actually do this from right to left. So do 1, then you do 2. Right, so obviously we shall discuss this in detail, but now if you do row 1, it is row 2. Row 1, row 2 becomes the identity. Shall discuss this in detail. Row 1, mu1 is mu3. Okay, some of these we've already seen. Like, yes, like this one. We discussed row 1, mu1, right? Because what did you say? We discussed it here. So when discussed row 1, mu1, like row 1, mu1 in this order, we saw that it is mu2. So we saw that row 1, mu1 is mu3. Row 1, mu1 is mu3. Mu1, row 1 is mu2. So row 1, mu1, row 1, mu1 is mu3. We saw that. Anyhow. So if we do mu1, row 1, right, so it is mu2 like that. Okay, so yeah, that's what we experimented this. So like if you then say mu1 for this one, mu1, row 1, mu1, row 1 is mu2. Let's do row 1, mu1. In other words, we're doing row. Okay, one student asked me to say, what is this symbol here? Right. So we're doing row 1, mu1. So if you're doing row 1, mu1, we saw that it is mu3. So as a consequence, then obviously we actually were able to see how these are the case. So how do you know that row 1 mu1 is mu3? You actually test these things. So you do row 1 mu1, you take it on A, and then you do row 1 mu1 on B. On the vertices, row 1 mu1, you do it on C, and then you see the images, and then you see exactly that it takes us to a given permutation. Okay, a given permutation. Okay, so we continue. We continue. All right, we continue. Okay, so you're done, right? Let me check. Okay, right. So we good, 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 we good. Right, good. All right, so you can play your things. Right, so now let's do some definitions and examples. So the integers modulo n and the symmetries of a triangle. Okay, now we have a chance. First, we did the integers modulo n, and we did the symmetries of a triangle, not only of a triangle, but or a rectangle are examples of groups. These are examples of groups. Okay, because in the K-leg table here, we're able to see inverses, like the inverse of row 1 is row 2. You look for the identity here. The inverse of row 3 is of mu3 is itself mu3, because that's when you get the identity. All right, now let's say the integers modulo n and the symmetries of a triangle or a rectangle are examples of groups. A binary operation or law of composition on a set G is a function from G cross G to G that assigns each pair AB element of G cross G a unique element as a composition of A and B, or A, B in G, called the composition of A and B. A group G with the composition, with the law of composition, or what you call a binary operation, which obviously becomes a law of composition. So a group G with the law of composition is a set G together with a law of composition such that A, B is taken to the composition of A and B such that, that satisfies the following axioms. What are the axioms? So these are the group axioms, right? The group axioms are the law of composition is associative. So obviously for the law of composition, it is associative. So if you associate A and B, C outside, it's the same as associating B and C, A outside. For A, B, and C in G, there exists an element E in G called the identity element, such that any element A in G yields the following. So you have the composition of E and A is equal to the composition of A and E, which is equal to A. So there exists an element E, element of G, called the identity element, such that for any element A in G, you have that the identity is fixes A. So the composition of, by the law of composition of E and A is the same of the law of composition of A and E, and we get A. Right, for each element, A in G, there exists an inverse element in G, denoted by A inverse, such that you can take the law of composition, apply it to A with its inverse, A inverse with A, and the result is the identity. First, we get the identity. The identity is E. So after we got the identity, then we say we can speak about the inverse element in G, denoted by inverse. Okay, we're here to solve problems, please, where these things are used in the kinds of the TAT problems and things and the past tests and so on. Right, so we're going on to then say a group G with the property that the composition of A and B is B and A for all A, B, and G is called abelian or commutative. So yeah, there's a group that is called abelian or commutative where A, B, the composition of A and B is the same, is equal to the composition of B and A for all A, B, and G. It's called abelian or commutative. It's called abelian or commutative. It's called abelian commutative. Groups not satisfying this property are said to be non-abelian. Groups not satisfying this property are said to be non-abelian or non-commutative. Okay, there's groups that are called commutative, there are groups that are called non-commutative, there are groups that are called abelian, there are groups that are called non-abelian. After Abel, a French mathematician. Okay, now let's discuss the Cayley table in relation to the integers modulo n and the integers in general, but also the symmetries of triangles and rectangles. Let's look at the example 3.8. So the integers z, which are -1, 0, 1, 2, and so on. This is all the integers, not only modulo something. Form a group under the operation of addition. So in other words, we define a group z plus like this. So we define a group z plus like that. The binary operation on two integers m n is just their sum. Okay, so we continue. So the integer z form a group under the operation of addition. The binary operation on two integers m, n, and in z is just their sum. Okay, so find their sum. The sum of m plus n and the m plus n is an element. M plus n together, when you add them up, you get an integer. Just the sum. Since the integers under addition already have a well-established notation, we will use the operator addition instead of the composition. So instead of speaking about the composition for the integers, instead of saying and the composition of m and n, we're going to use addition there for the integers. All right, so instead of that, the identity is 0. The identity is what? Is 0. And the inverse of n in z is written as minus n instead of n inverse. So in other words, obviously for the integers, we know that this is a negative number, you know, under addition. So we don't even write the multiplicative inverse for it. We understand the integers better. Note that the set of integers under addition have the additional property that m plus n is n plus m, and therefore form an abelian group. So now we acknowledge the fact that these integers are very wonderful, but they form an abelian group, or what you call a commutative group. Right, most of the time we'll write AB instead of the composition of A and B. However, yes, so most of the time we'll write AB for most of the groups, because just write AB like this to understand that there's an operation there that operates. So most of the time we'll write AB instead of the composition of A and B. However, if the group already has a natural operation like the integers, such as addition in the integers, we will use that operation. If we are sure what the operation is, then you can write A plus B. Otherwise, you can just write AB. Then we discuss this kind of group, and yeah, but obviously in this module, yeah, you have lots of in this module you have seen in the past exams, it's not only multiplicative groups, but you have lots of additive groups. The additive groups module or whatever, they come in the exams. So yeah, that is, if we are adding two integers, we still write m plus n minus n for the inverse and 0 for the identity as usual. We also write m minus n instead of m plus minus n. Instead of writing m plus minus n, we write m minus n. But you understand that it is addition, this m minus n. We saw that in the past exam paper we discussed. So instead of the m minus n, we write, yeah, instead of m plus minus n, we write m minus n. It is often convenient to describe a group in terms of an addition or multiplication table. It is often convenient to describe a group in terms of an addition or multiplication table. Such a table is called a Cayley table. Sometimes we can just convenient to describe. So this Cayley table describes a group in terms of addition or multiplication table. Sometimes you can describe a group by drawing its Cayley table. Then it's a way of saying we're describing a group. Let's look at example 3.9. Check for me this time, please. Example 3.9. Okay, that's fine. Example 3.9. So the integers modulo n form a group. Okay, like the Cayley table of Z5 under addition. So the integers modulo n form a group under addition modulo n. Consider Z5 consisting, okay, Z5 because the 5 is prime. The 5 is prime, and this is very important for the groups. All right, and now we're gonna be looking at this Zn, where n is prime. What kind of groups are these? Versus when n is composite. When n is a composite integer, where n, you see, sometimes it's prime, like 5 is prime, but it can be composite like Z6. Z6 is composite because 6 is 6 by is 2 by 3, for example. You know, it's a composite number. So let's just look at just this example in passing. In example 3.9, the integers modulo n form a group under addition modulo n. Okay, consider Z5 consisting of the equivalent classes. Very important. Look at how the author of the book presents this example. He says you consider Z5 consisting of the equivalent classes of the integers 0, 1, 2, 3. So this Z5 consists of the equivalence classes. We define the group operation on Z5 by modular addition. So we write the binary operation on the group additively. That is, we write m plus n. The element 0 is the identity of the group, and each element in Z5 has an inverse. For instance, okay, let's continue. Okay, let's continue. Let's continue. For instance, right, so we continue. For instance, 2 plus 3 is equal to 3 plus 2 equals 0. So yeah, so now we're saying the element 0 is the identity of the group. And each element in Z5 is an inverse. This is very important. And each element in Z5 has an inverse. We saw that in Z12, it was not the case. In Z12, it was not the case. So here it is the case. So we are noting that, yeah, for instance, here there is the, okay, we're going to analyze that. So for instance, 2 plus 3 is 3 plus 2, commutative, and this is 0 in modulo 5. Figure 3.10 is a Cayley table for Z5. By proposition 3.4, we saw proposition 3.4 went through together about the addition that's commutative, the multiplication that is commutative, associative, and so on. So by proposition 3.4, Zn would be 0, 1. Zn would be 0, 1 up to n minus 1. Okay, because we have n here, it will go up to n minus 1. We have n here, it goes up to n minus 1. It's a group. This Zn is a group under the binary operation of addition modulo what? Under group operation of addition modulo n. Right, Cayley table for Z5 plus. But what are we able to see for the prime 5, Z5? Where 5 is prime, there's a 1 here. 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 Okay, it tells us that the multiplicative inverse, it tells us, okay, this is the addition additive one. So, but also in the additive one, okay, I wanted to, I'm going to comment about the multiplicative Z5 group. But now under addition, so you have 0 there, you have 0 there, you have 0 there, you have 0 there, you have 0 there. What does this mean? This means that the inverse, the additive inverse of 0 is 0. The additive inverse of 1 is 4, because 1 plus 4 is 0. And the additive inverse of 2 is 3 because 2 plus 3 is 3 plus 2, which is 0. The additive inverse of 3 is 2, 3 plus 2 is 0. The additive inverse of 4, 4 plus 1 is 0. So this is the Cayley table for Z5 plus. Cayley table for Z5 plus. Cayley table for Z5 plus. We continue. Okay, let us look at this example, which is example 3.11. Not every set with a binary operation is a group. You can have a set with a binary operation that is not a group. For example, if we let modular multiplication to be the binary operation on Zn, then Zn fails to be a group. For example, if we let modular multiplication be the binary operation on Zn, so if we look at multiplication, because we're looking at addition in Z5, but if you want to look at multiplication, right, then Zn fails to be a group under multiplication. The element 1 acts as a group identity since 1 by k. So we're looking at the at the element 1. 1 by k is k by 1, which is k for every k in Zn. We continue. Okay, so however, a multiplicative inverse of 0 does not exist. Okay, this is the reasoning by the person who wrote the book, the author of the book. So the multiplicative inverse of 0 does not exist. Why? Since there's no number that can multiply, since if multiply 0 by any number, k is 0 by k is k by 0, which is 0 for every k in Zn. Even if we consider the set Zn and we remove 0, we still may not have a group. For instance, okay, this guy is saying sometimes this Zn, it fails to be a group. Zn fails to be a group in many instances under multiplication, right? So now if you take Zn and you remove 0, we still may not have a group. For instance, if you take 2 in Z6, then 2 has no multiplicative inverse. Why? Because 2 has no multiplicative inverse because 0 times 2, so you can multiply 2 by all the numbers in Z6. Right? If we then say we want to find the multiplicative inverse of 2 in Z6, which is 0, 1, 2, 3, 4, 5. Right? We stop at, remember that for Zn, we stop at what? Zn, we have 0, 1, 2, and we stop at n minus 1. Right? So we stop at n minus 1. But then, obviously, so we stop at 6 minus 1, which is 5. So now, then 2 has no multiplicative inverse. Why? But let's check. So we get 2. We want to check the multiplicative inverse of 2. So we multiply 0 times 2. We get 0. Then we take 2 times 2. Okay, now the author of the book went across like this. So 0 times 2, it's 0. Then you take 1. 1 times 2 is 2. So want to check if it has a multiplicative inverse so that 2 must produce 1 in Z6. Okay, then we have 2. 2 by 2, it's a 4. 3. 3 by 2, it's 0. 4. 4 by 2 in mod 6. 4 by 2 is 8, but it is 2 in modulo 6. Right, then we have 5. 5 by 2 is 4. We can see that after multiplying 2 with all these numbers, 0 times 2, 1 times 2, 5 times 2, all of them do not give 1. So in other words, then 2 has no multiplicative inverse in Z6. Move on. Let us actually now mention the notion of proposition 3.4. Every non-zero k does have an inverse in Zn. Okay, we saw proposition 3.4. But by proposition 3.4, every non-zero k does have an inverse in Zn if k is relatively prime to n. So if k is relatively prime to n, then you can get the inverse. K does have an inverse. So you can get the inverse of K if K is relatively what? Prime to N, and yeah, that takes us to that. So we'll discuss the group U8, for example. Denote the set of all such non-zero elements in Zn. Okay, this is very important. Denote the set of all such non-zero elements in Zn by Un. Right, then Un is a group called the group of units of Zn. The group of units of Zn. In figure 3.12, figure 3.12 is a K-lay table for U8. Right, let us check U8. Okay, let us discuss U8 together. So we can see that U8 is a group of, right, it's a group called the group of units of Zn. The group of units of Zn. The group of units of Zn. So in other words, we are dealing with the group of units of Zn. So now let us deal with the group of units of Zn. How do we find the group of units of Zn? So this group of units of Zn, U8, how do you know the elements in this set? Because we're saying the elements are 1, 3, 5, 7, but I want to discuss how we arrive at these, right? Because this is the author indicated here that every non-zero K does have an inverse in Zn if K is relatively prime to N. Denote the set of all such non-zero elements in Zn by Un. So we shall look at Z8. Z8 is 0, 1, 2, 3, 4, 5, 6, 7. This is Z8. Let us look at U8. Right. So now denote the set of all such non-zero elements in Zn by Un. Right. So now we're looking at the group of the units. So now every non-zero K does have an inverse in Zn if K is relatively prime to N. So we look for the integers that are relatively prime to N. So let us look at these. What are the integers that are relatively prime to 8, for example, in this set here? So if you look at the fact that is 0 relatively prime to 8, it is not. It's 1 relatively prime to 8. Yes. So we put 1. Is 2 relatively prime to 8? Well, relatively prime means the greatest common divisor of 8, and that integer must be 1, then is relatively prime. So, for example, if you look at the greatest common divisor of 0 and 8, what is the greatest common divisor of 0 and 8? Right, we can see that the greatest common divisor of 0 and 8 is 8 itself. So in other words, we want the greatest common divisor to be 1. So yeah, so now this one is out. It's 1. The greatest common divisor of 8 and 1. Right, so the greatest common divisor of 8 and 1 is just 1. So we take the 1. The greatest common divisor of 8 and 2 is 2, so 2 is out. The greatest common divisor of 3 and 8, the greatest common divisor of 4 and 8, because the greatest common divisor of 8 and 4 is what? The greatest common divisor is 4 of these two numbers. So now we can see that 4 is out, but 3 there. 5, yes. 6, no. 7, yes. So now that is why, therefore, we're able to see U8. Now, this is the K-lay table, the multiplication table for U8, which is 1, 3, 5, 1, 3, 5, 7. Then 1, 3, 5, 7. Then you multiply. 1 by 1 is 1. 1 by 3 is 3. 1 by 5. 1 by 7. 3. 3 by 1. 3. 3 by 3. Because this U8 still has to do with modulo 8. Modulo 8. So in other words, if you say, for instance, 3 by 3, it's 9. In modulo 8 is 1. 3 by 5 is 15 in modulo 8 is 7. 3 by 7 is what? Is 21. In modulo 8 is 5. And so on and so forth. So this becomes the multiplication of for multiplication table for U8, which is the group of units of Zn. So this U8 is the group of units of Z8. It's U8. Like that. Okay, so now what are units? Units are all those elements that have multiplicative inverses in Z8. Okay, let me check. What is the check for me the time, please? Okay. We're gonna discuss this example here. Let's discuss the symmetries of an equilateral triangle described in section 3.1. Right, form a non-abelian group. So we are saying that the symmetries of an equilateral triangle, what do they form? These symmetries form a non-abelian group. As we observed, it is not necessarily true that alpha beta for the triangle is the same as beta alpha for two symmetries, alpha and beta. Using figure 3.7, which is a K-lay table for this group. We did the K-lay table for the symmetries of a triangle. We called it figure 3.7, which is the K-lay table for this group. We can easily check that the symmetries of an equilateral triangle are indeed a group. So yeah, the symmetries of an equilateral triangle form a group. We will denote this group by either S3 or D3 for reasons that will be explained later. Okay, so the symmetries of an equilateral triangle are indeed a group. We will denote this group by either S3 or D3 for reasons that will be explained a little bit later on. Right, I think that we have discussed sufficiently. We shall continue in our next appearance. In our next appearance, we shall continue and look at more notions of this nature in as far as our groups are concerned, but I shall look at a lot of the charts and other things.